Hello viewers and my dear students. Welcome to session 4 of problem 5 on analysis of beams. Here I am showing you a demo on overhanging beam with moment using Ansys Mechanical APDL to obtain bending stress and deformation diagrams. As you know already, this is session 4. In session 3, we have completed the model. In fact, we have got the solution also. Okay, only thing is we have to go to general post-processing now. Okay, now as you know here, the problem is this. The problem was this. See here, this is the bending stress. Maximum bending stress is 2 into 10 to the power of 6, 2 MPa. That is, this is the bending stress diagram to be obtained here. And since in the bending moment diagram, this is 6,000 Newton meter, this is also 6,000, this is also 6,000. Everywhere it will be 2 MPa, minus 2 MPa, minus 2 MPa in that way. This is the bending stress diagram you have to get. You have to get exactly 2 MPa. This is the theoretical answer. Our Ansys result should be very close to this. Only this part is remaining now. Okay. Now you see here. Now we have solved this problem. Okay, we have solved. Now we have to go for general post processor. Okay, that is solution phase is, that is pre-processing phase is over. Solution phase, applying the loads here and all that we have seen, and we have applied the loads at the right points and all that, and we have even solved that. Okay, and if you want to check this, you see here, list right from that, you know very well, key coordinates only. Okay, you just say 1 is 0, 0, 0, 2 is 2, 0, 0, 4, 0, 0, 6, 0, 0, 7, 0, 0, and 7 minus 1. This is the orientation point. This also. Everything is proper here. This is okay. Then list. Now properties, if you go, all materials, you can see that there is only one property, that is steel, that is 2.111 or 0.21 into e to the power of 12. Okay, this is this is 210 GPa. That means this is 0.21 into 10 to the power of 12 Newton per meter square it is. That is why, and this is Poisson's ratio, and since it is in Newton per meter square, all I have done it in the modeling, I have done it in meter, and the loading I have done it in that is Newtons. Okay, then if you see, if you want to see here, I'll just plot controls, numbering, key point numbers, let us say I'll make it on. Okay, this is 1, 2, 3, 4, 5 key points, correct? No? Key point numbers I have made it on. Now you see here, list, loads, DOF construction on all key points, let us say I'll do. See here, carefully you see, I have fixed here, correct? No? 1 and 4. 1 use UX, UY, UZ, rotation X, rotation Y. It is all 0 except rotation Z. At 1, this is key point 1. And at the same time 4. 4 also, UX, UY, UZ, rotation X, rotation Y. It is perfectly okay. At 1 and 4, we have fixed the beam. Okay, except rotation Z, I have fixed in all respect. Okay, then you have loaded at 2, you have loaded at 3, you have loaded at 5. That also you can verify. List, loads, forces on all key points you see. See here, if you see on all key points, at node 2, here it is MZ, 12,000 Newton meter. Correct? No, correct, it is 12,000 Newton meter. Fy on no key point 3, it is minus 3,000. And key point 5, it is minus 6,000. Both 6,000 only, minus 6,000. That is on 3 and 5, it is minus 6,000. In that way, this is also proper. Okay. Did you follow? And also you know very well, even if you controls here, plot controls, style, size and shape, display element on. If you say OK, plot elements, and if you do this, you are having the orientation proper. See here, this is 0.2, this is 0.3. I am enlarging it and showing it to you. See here, this is 0.2, this is 0.3. Orientation is proper. In that way, you don't have to worry at all. What we have done is perfectly okay. Plot controls, symbols, all boundary conditions. Okay, if you say, you see here, there is one load here, there is one load here, and this will represent moment, okay, or couple. In that way, if I go to the front view also, it is all correct. Okay, orientation is proper, loading is proper, everything is proper. Okay, now plot controls, style, size and shape, display element off. I'll just say okay, and then once you have done this, okay, now I have already solved this. No solution solved, current LS is over already. Now I'll go for general post processing. See here, solution, that is pre-processing phase is over, solution phase is over, that is I've already solved. Now I'm going for post processing. First, what you have to do is, whether you've done correctly or not, check immediately under list results reaction solution. Reaction solution, all items you see here clearly, you see at node 1 it is 3000, and this is node 102, it is 9000. That also you can see. If you want to see plot controls numbering, okay, node numbers on, if you do, you will get all node numbers now. Okay, in that way you can see 102. Okay, you can see 102. You see here. This is see here. This is 102. Okay, I'll just enlarge it here. I'll enlarge it here. This is 102. That should be at that node number. It should be 9000. Okay. Now we'll see plot controls, numbering, node numbers on. If I do plot, multi-plot, see here 102 exactly. Did you follow? This is 102 exactly. At 102 also it is 9000. Correct? No? And the first node, as you see here, first node also it is 0. In that way, plot elements you go, and then plot controls, numbering, node numbers you make it off, everything is okay. Now once you have got this is one of the very important results. First you copy down this one, that is reaction solution at node number 1, 102, FI 3000, 9000, what we have got theoretically, that should match. Then important thing is you go for element table. Element table, because we are interested in bending stress. The bending stress should be approximately 2 MPa. We have got this by theoretical method. Same thing you should get by Ansys method also. Define table, add you do by sequence number. Define table, add by sequence number, SMISC 34 you do, apply you do, then by sequence number SMISC 39 you do, you say okay. That means this is item, this is sequence number. SMIC 34, SMIC 34, SMIC 39. If you have item and sequence number like this, you are getting the bending stress diagram. Okay. Now what you do is you go for plot results, contour plot, line element results, 34 and 39 you go and say this exactly you see here. This is red you see 0.196 into e to the power of 7 or 1.9 into 10 to the power of 6. That is 1.9 MPa. Correct? No? 1.9. But actually we should have got 2 MPa. But I have told you, if you divide this into more number of equal parts, That is here, since we have done 25, 25 here, if you make 50 or 100, it will be almost 2 MPa only. Now it is almost correct. You see here, 0.196 e to the power of 7 or 1.96 into 10 to the power of 6 or 1.9 MPa. Okay, even negative also. Okay, point same thing you get, because everywhere in the theoretically everywhere it was same. Here also 0.196 into 10 to the power of 7 or 1.9 MPa. Here also 1.9 MPa, 1.9 MPa, 1.9 MPa. The theoretically what we had got, same thing we have got it here, but only thing is theoretically we had got 2 MPa. Now it is 1.96 MPa. In that way, this also is a very important thing what you have to record. That means you go to plot controls, write meta files, invert white and black, have it in paint. Okay, have it in paint. This is another important thing what has to be stored, or show it to the examiner, or copy it and paste it in your records, or draw the same thing in your examination answer sheets. Same, this is the bending stress plot. Show that this is 2 MPa, this is 0.196, that is 1.96 MPa, 1.96 MPa, 1.96 MPa by Ansys methods. Same thing you draw again, by theoretically you have already got 2 MPa, 2 MPa, 2 MPa, 2 MPa. Small error is because of the number of divisions. That can be attributed. That means this is one thing. Then see here, another important thing is deformed shape. Deformed plus undeformed. You see here, perfectly you should get this way. Okay, perfectly you should get this way. There is a deformation here, there is a deformation here, and all that. Because of the moment and the loading, this has deformed in this way. Okay, the blue is the deformed one, that white is undeformed. Okay, in that way, deformed and undeformed also, we have got it properly. This is another very important thing. What you have to, write meta file, invert white and black. This also you store it and say the maximum deformation is 0.929 into 10 to the power of minus 4 meters. 0.929 into 10 to the power of minus 4 meters is the maximum deformation what is occurring, maybe here. Okay, you can always verify by going to list results and finding the nodes. At this node, at which node it is, 0.929 into 10 to the power of 4. You just have to go to the list results and nodal solution. If you go, DOS solution, displacement vector sum, you get this, and you know very well it is 152. Okay, node number 152 is here, 0.929 e to the power of minus 4. It is node number 152. Okay, now you make node numbers on and say where exactly is 152. At that particular point, you have so much is the deformation. Okay, plot controls, you should know numbering, node numbers, this node number should be on. Okay, and in that way you test it. Where exactly is the maximum deformation? This has to be that. Okay, now the important things I'm telling you again. The first results is list results, reaction solution, all items immediately. This has to be verified. 3000 and 9000. Okay, this is one important thing. Immediately record. This is the first result. And next one is plot results, deformed shape, deformed plus undeformed. You get it. This is another thing. 0.929 into 10 to the power of minus 4 is the maximum deformation. You write the same thing in the exam also. You can use your pencil, pen and all that. Make it as neat as possible. You give the same curve. This is more than enough. That people will appreciate. Okay, in the same way, contour plot, line element result, SMISC 34 and 39 you say, and exactly this way. You write, and you write 1.96 MPa here, 1.96 MPa, 1.96 MPa, you write it here, and this also you can write it in your answer sheets only. You can write the same thing. You can write it, you copy the same thing and say 1.96 MPa, 1.96 MPa, 1.96 MPa, here 0, 0. In that way, three important results we have got. Okay. In that way, we have completed this problem in all respect. Okay. Now we have come to the end of session 4 and we have completed this overhanging problem in all respect with moment also. We have completed bending moment shear force diagrams in first 2 sessions, and in third and fourth session we have completed bending stress diagram and actual deformation plot also. Thank you friends. Thanks for watching. Thank you.